G'day chemistry students. In this video, we're going to be covering dot points 4.3.5 and 6 again. We're doing some more Gibbs free energy calculations, but this time we're using some literature data to find delta H and delta S. Let's get into it. So first off, when we start using these standard values, you're going to find that they look something like this usually. You'll see that they have a Greek letter theta. So either a circle just sort of sitting at the top, similar to a degree symbol. Maybe it might have a line through it, but these symbols represent that we are working with standard values, values that have been experimentally determined and then included as literature data to use in theoretical calculations. So the first one here is our standard enthalpy of formation. We've actually learned about this already when we were looking at our Hess's law concepts. The enthalpy of formation is defined as the energy required to form a compound from its elemental components. So we can use these standard values in calculations to find the delta H of reaction. We can also use or find data about the standard molar entropy. So the idea is for a given substance, what is its entropy if you had a mole of the substance under what we would call standard conditions. So in other words, 25 degrees Celsius. So with those two pieces of data, we can actually begin to calculate the enthalpy and entropy changes in a reaction separately. So using enthalpy of formation data, knowing what the enthalpy of formation of all the products are, and then taking away the enthalpy of formation of all the reactants, we can find the enthalpy of reaction. And for entropy of reaction, if we know the entropy of all the products and the entropy of all of the reactants, we can find the entropy of reaction using all of that standard data. So really, this just goes back to our definitions of what delta S and delta H actually mean, but we're applying that with literature data in these questions. So just to note, you can have these kinds of tables that show our standard values, enthalpy or entropy. Please note that you won't see any of this on your data sheet. If you do need to do any calculations with this data, you will be given it you'll be given it in the question. So you don't have to worry about memorizing any of this or anything like that. If you need it, you'll get it. It's not in the data sheet, so you don't have to refer to that for these questions. But anyway, let's go look at how to apply some of these tables to a Gibbs free energy calculation. So in this calculation, we're being asked to determine if the reaction below is spontaneous under standard conditions, given the standard tables of enthalpy of formation and molar entropy, which I've got above. So in this reaction, we're starting with 2 moles of NO2, and it's decomposing, breaking down to form 2 moles of NO and 1 mole of oxygen gas. So to approach this question, we're still going to need to calculate Gibbs free energy. That's still going to be something that we are required to do because we're still being asked to find out whether or not the process is spontaneous or non-spontaneous. The big difference here is we haven't been given all the information outright to do it like we did in the first calculation that we did in the previous video. So we're still going to write up our Gibbs free energy equation because we're still going to be using that. So the change in Gibbs free energy is equal to delta H minus T times delta S. Now the only value that we've been given so far technically is delta T because we've been told that we're working under standard conditions. That's 298 degrees Kelvin. And we know that because standard conditions are 25 degrees Celsius. And to convert that to Kelvin, we need to add 273 additional degrees. For the rest of it, though, we've got to take a little bit of a different approach using some of the concepts that we've gone through in the slides. So we need to be using our delta H of formation, so our enthalpy change of formation for all reactants. And we know that we can find that if we know the enthalpy of formation for our products. And we subtract the enthalpy of formation for our reactants. Let's fix that. And so we can then try and find those enthalpy of formations in our tables up here. So first off, we're looking at our products. Our first product here is 2 moles of NO, and I can see that in the table as well. We have NO here, if we have 90 moles of NO, its enthalpy of formation is plus 90 kilojoules per mole. Because we've got 2 though, or 2 moles in our equation, we have to take that into account when we are calculating down the bottom here. The next product that we have is O2. And you'll notice in all of these enthalpy of formation tables, which are all of these ones here, that really there isn't anything elemental present at all. You've got your ions in aqueous solution, but technically they're not exactly an element in this case. Or most things here are compounds anyway. There's a couple of examples here, the iodine and the O3, that aren't. But generally speaking, O2 is the way that we find oxygen as an element in a natural system. So when we're looking at energy changes and we're looking at the definition of enthalpy of formation, what we're really saying is how do we form a new molecule from its elemental components? And because O2 always exists, because oxygen always exists as O2 naturally, we actually use O2 rather than just a single atom of O in our thermodynamic data. So when we're looking at any of this stuff, we always treat elemental oxygen as O2. And because there's no energy required to form one of those elemental components, its value is 0 here. So the enthalpy of formation for O2 is always going to be 0 because it's in its natural elemental state. When we look at the enthalpy of reactants, though, we need to be looking at the 2 moles of NO2 that we've got. And we can find that on the top here. So a mole of NO2 has an enthalpy of formation of 33 kilojoules per mole. And because we have 2 moles in our equation, we've got to multiply that by 2. So 2 times 33. To do the math, then we've got 180 minus 66, and that's equal to 114 kilojoules per mole. So something that I just noticed is that I actually wrote reactants up here. That's my mistake. It should say enthalpy of formation for reaction. But the next thing that we need to do anyway is to find delta S using our standard entropies, or our standard molar entropies in particular. So we need to find that for the entire reaction. So we can use the data that we've got up in our table at the top, but delta S, standard one for products. And all of our products, you'll see that there is one for oxygen for entropy, and standard entropy, molar entropy for reactants. So let's go have a look at the top. So we'll do our products first. So that's our O2 and NO. We have 2 moles of NO, 1 mole of O2. So when we're looking at that, we've got 205 for the oxygen and 211 for the NO. So putting that into our equation, that will look something like this. So 2 times the NO plus the 1 mole of oxygen. And then we're going to take away the molar entropy of the reactant. So that's just for our NO2. We've got 2 moles of that. So having a look over here, our NO2, it's 240. So the NO2 is 240, so 2 lots of 240. So then when we actually go in and do the math, that's going to turn into 422 plus 205 minus 480. And that comes out as 147 joules per Kelvin per mole. And so notice that the units are slightly different because they reflect an entropy. They are, as it says up here, joules per Kelvin per mole. So that's been shown here too. Note though, in particular, there's a little bit of a discrepancy, the joules and the kilojoules here. So to fix that, I'm going to be converting my my entropy into kilojoules. So that's 147 times 10 to the negative 3 kilojoules per Kelvin. per mole, per mole. And so then with all of this data, we now have our delta H, T, and delta S to be able to calculate G here, our Gibbs free energy. So I'm going to rewrite that equation, substitute in all my values. So delta G for our reaction is equal to delta H, 114, minus T, which is 298, times delta S, which is 147 times 10 to the negative 3. When we put all of that together, and with our delta G down the bottom here, it comes out to be 70.2 kilojoules per mole. Note as well, because we were using values with our standard enthalpies of formation that had two significant figures, that should be the same here as well. So 70 kilojoules per mole. And with this, we've calculated delta G. We've found that the value is positive, and that we know that for positive delta Gs, the reaction that it represents is going to be non-spontaneous. So I'm going to write delta G is positive. Therefore, process or our reaction is non-spontaneous. And there we have it, a process using literature data for standard values of enthalpy and entropy to be able to determine whether or not chemical processes are spontaneous or non-spontaneous. Thank you very much, everyone. With the conclusion of this video, this means not only have we ended Module 4, but we have also done all of the content for this Year 11 HSC course. Congratulations, well done. Give yourself a pat on the back. You guys have been working fantastically so far through this first part of the course. With whatever time we have left in the term, we'll start doing a little bit of revision in preparation for your yearly exams. And I can't wait to catch you in Module 5 to begin the real meat and potatoes of this course, all in preparation for your HSC. But until then, have a good one.